Right now, as you are hearing this, every bank transaction on Earth is protected by a single mathematical principle. Every military command, every encrypted message between heads of state, every medical record with your name on it, every nuclear launch code, all resting on one principle. 3 mathematicians at MIT discovered it in 1977, and for nearly 50 years it held. It held because it relied on a task that no machine in existence could perform. Not slowly, not with difficulty, but in the absolute sense of the word, impossible. The entire digital architecture of human civilization was built behind this wall. Your passwords, your savings, the communication lines between submarines carrying warheads, all of it, locked behind the same door, using the same key, trusting the same assumption, that the wall would hold. It is not holding. A crack appeared. It was small at first, theoretical, a line in a physics paper that most people never read. Then, the crack widened. Laboratories started reporting results that should not have been possible. Machines started solving problems that no classical computer could touch. The crack did not grow slowly. It jumped. And somewhere between a Google laboratory in Santa Barbara and a research paper published in late 2024, the fracture became a hole. We did not notice the exact moment it happened. That is the nature of walls. You trust them precisely because you do not watch them. You go about your life assuming the structure is sound, and you only discover the breach when something falls through. Something is falling through right now. And to understand what it is, we have to start with the moment a machine did something that should have been impossible. The first fracture appeared in a laboratory in Santa Barbara, California, in the fall of 2019. Most people missed it. A machine called Sycamore, a processor with 53 qubits sitting inside a refrigerator colder than outer space, was given a problem. Not a useful problem, not the kind that changes your life, but a mathematical puzzle specifically designed to answer one question. Can this machine do something that no classical computer can do? Sycamore finished in 3 minutes and 20 seconds. The same task, on the fastest supercomputer that existed at the time, would have taken roughly 10,000 years. Let that land for a second. 10,000 years. That is the entire history of civilization. Every empire that rose and fell, every war, every cathedral built by hand, every book written, compressed into the time it takes to boil an egg. A physicist at Caltech named John Preskill had a word for this moment. He called it quantum supremacy. Not because the machine was faster, since faster implies the same road with a quicker car, but because this was a different road entirely, a road that classical computers cannot even see, let alone drive on. And then, the world moved on. A pandemic hit, elections happened, and people forgot. But the physicists did not forget, because Sycamore had not done anything useful. It had done something much worse. It had proven that the road exists, that a quantum machine can reach places where classical machines simply cannot go. The task was a toy, but the road was real. And if you could make it more stable, if you could fix the one brutal problem that kept it from scaling, you could drive that road straight into the wall that protects every secret on Earth. The problem was noise. A qubit is the most fragile object humans have ever tried to engineer. Think about that. We build skyscrapers in earthquake zones. We land robots on Mars. We split atoms. But a qubit makes all of that look crude. Because a qubit holds its information in a quantum state so delicate that a single stray photon, a vibration you could not feel if it hit your hand, a thermal fluctuation so small it does not even have a name in everyday language, any of these can destroy it. Gone, the information simply vanishes, not corrupted, not degraded, but erased entirely, like a soap bubble touched by a fingertip. And here was the nightmare. To solve harder problems, you need more qubits, but more qubits means more things that can go wrong. Every qubit you add is another soap bubble in the cluster, another surface exposed to the universe, another chance for the whole thing to pop. For decades, this was the wall. You could not build a useful quantum computer because the system drowned in its own noise before it finished thinking. In 1995, a mathematician named Peter Shor, and you will hear his name again very soon for a much darker reason, proved something on paper. He showed that quantum error correction is possible, that you can design the system so that adding more qubits actually cleans up the errors instead of multiplying them. The theorem was beautiful, and it sat on paper for 29 years because no one on Earth could build it. Then, in December 2024, Google published results from a new processor called Willow, and the curve flipped. For the first time, more qubits meant fewer errors. 29 years of trying, and the barrier gave way. Not in theory, but in silicon. In a laboratory you could walk into and touch. The soap bubbles stopped popping. The machine could now grow. And a machine that can grow can eventually run any algorithm you feed it, including one very specific algorithm that has been waiting in the open literature for 30 years, like a loaded gun sitting on a library shelf. It was built in 1994. The same Peter Shor, working at Bell Laboratories in New Jersey. Bell Labs, the place where the transistor was invented, the place where the theory of information was born. Shor was not trying to build a weapon. He was curious about a math problem, a simple one actually, so simple that you can explain it to a child. Take two numbers, multiply them together, easy. Your phone can do it in a fraction of a second, even if the numbers are hundreds of digits long. Now reverse it. Take the result and figure out which two numbers made it. This sounds like it should be just as easy. Multiplication backward, except it is not. It is so far from easy that it sits in an entirely different universe of difficulty. For a number the size used in modern encryption, the best classical algorithm would take longer than the age of the universe to find the answer. Not a long time, but longer than everything. Longer than the stars themselves. Shor found a way to do it on a quantum computer in an afternoon. Not by brute force, not by checking every possibility, by exploiting a property of quantum mechanics that allows the machine to walk every path simultaneously and cancel out the wrong answers through interference. We will get to how that works. Right now, what matters is what it means. Because this asymmetry, the gap between multiplication and factoring, is not a curiosity. This is the bridge. The bridge your bank drives across. The bridge your government drives across. The bridge that carries the nuclear codes. And Shor's algorithm is a clean, elegant, mathematically proven way to collapse it. The algorithm has been published for 30 years. Anyone can read it. It is not classified, it is not hidden, and it has been sitting in plain sight, harmless, because no machine existed that could run it. Sycamore proved the road exists. Willow proved the machine can scale. The gun is loaded. The window is closing. The bridge is the target. And the bridge carries everything. So what is this bridge made of? Why is it so important? And why did everyone trust it for 50 years? The answer starts in 1977, in a room at MIT with three guys named Ron Rivest, Adi Shamir, and Leonard Adleman. They were playing with prime numbers. Not because anyone told them to save the world, but because prime numbers are strange and beautiful, and they wanted to see what would happen if you used them as locks. What they found was a trick so elegant, it almost feels like cheating. Take two prime numbers, hundreds of digits long, multiply them. A calculator does that in a blink. Now reverse it. Find the two primes from the product. The universe plays a joke on you. Going forward is instant. Going backward is impossible. Like shuffling a deck in 2 seconds and then trying to unshuffle it by staring at the result. That would take longer than the sun has left to burn. Rivest, Shamir, and Adleman built a lock out of this asymmetry, published the product as the public key. To decrypt, you need the primes. Nobody can find them. The mathematics will not let you. Not in a million years. Not before the heat death of the universe. They called it RSA, 3 letters. And those 3 letters became the invisible flaw under the entire digital world. You are standing on it right now. Every time you type a password, you are trusting that floor. Every time a diplomat sends an encrypted cable, every time a doctor transmits a diagnosis, every time a missile system authenticates a command. The floor is the same floor, and it holds because one mathematical operation is easy in one direction and impossible in the other. Shor's algorithm makes it easy in both directions. The floor is the bridge. The gun points down. Now, here is where you expect me to say there is a backup plan. A second floor under the first one. Some other kind of math holding everything up in case RSA cracks. You expect that because it is the reasonable thing. No engineer builds a civilization on a single point of failure. Except they did. In 1985, two mathematicians working independently, Neil Koblitz in the United States and Victor Miller in Canada, developed something called elliptic curve cryptography, ECC. It looks different from RSA, uses curves instead of primes, runs faster, and the keys are shorter. If RSA is a heavy iron padlock, ECC feels like a sleek modern deadbolt. Different mechanism, different design, and surely a different vulnerability. Same vulnerability, because Shor's algorithm attacks the structure underneath RSA, a structure called the hidden subgroup problem. ECC sits on the same structure. The padlock and the deadbolt are the same metal, and the acid dissolves both. No second floor, no backup bridge. The entire digital world stands on a single assumption. Factoring is hard. Every protocol trapped behind that assumption. When it collapses everywhere. Like pulling a tablecloth out from under every dish on a table that stretches around the planet. You might think that at least gives us a race. The machine is not ready yet. We have time. We can swap the locks before the acid is finished. And that logic would be perfectly sound if the attack started in the future. It does not. The attack started years ago. There is a strategy in intelligence work that does not require any quantum computer at all. It requires patience and hard drives. It is called Harvest Now Decrypt Later, and it works exactly the way it sounds. You intercept encrypted traffic. You cannot read it, so you do not try, you just copy it, all of it. You fill warehouses with hard drives full of gibberish that you cannot decode, and you wait. You wait for the machine to mature. And the moment it does, you feed the archive in, and the gibberish turns into words. Think about that personally. Every encrypted email you sent 5 years ago, every bank transfer, every medical record. If it was intercepted, and storage is cheaper than the coffee you drank this morning per gigabyte, it is sitting in a vault right now, sealed and waiting for a key that does not exist yet but will, patient as stone, certain as mathematics. In 2022, the NSA released an advisory telling national security systems to begin migrating to quantum-resistant encryption immediately. That word, immediately. They know something about the timeline. You cannot re-encrypt the past. You can change every lock on Earth tomorrow. It will not matter for anything already intercepted. The past is in the vault. The key is being built. When it is finished, the vault opens backward through time, and every secret that ever crossed the wire becomes readable. All of it. At once. Now you're probably imagining a spy in a trench coat, tapping a single wire, copying a few important files. That is not what this looks like. The global internet moves roughly 400 exabytes of data every single day. That number means nothing to a human brain, so let me put it differently. If you printed it out on paper, the stack would reach the sun. Every day. Within that flood, there is a stream of encrypted traffic that carries real weight. Diplomatic backchannels, military logistics, intelligence chatter, financial clearing systems, energy grid commands, pharmaceutical research data. The stream is a fraction of the total. But a fraction of a number that reaches the sun is still enormous. And the infrastructure to tap that stream is not hypothetical. It has existed since the early 2000s. Fiber optic splitters, satellite intercepts, undersea cable taps, all feeding the same storage. Every day it runs, the archive grows, and encrypted data does not rot. It does not degrade, does not expire, and it sits in perfect mathematical fidelity, ones and zeros exactly as they were the moment they were copied, waiting. Stretch that across 15 years, and the value of what accumulates becomes obscene. A single diplomatic cable revealing a negotiation position can be worth more than you will earn in your entire life. A single military communication can redraw the balance of power in an ocean. There are not single cables in the vault. There are billions, layer after layer of frozen secrets, and the drill that will reach them is being assembled in laboratories you will never see. And this is what makes it different from every hack you have ever heard of. Every other breach exploited a mistake, a bug, a lazy password. This one exploits the mathematics. The lock was perfect, and it is going to be opened anyway. Because someone built a machine that operates by rules, the lock was never designed to withstand. Rules that do not belong to the world you and I grew up understanding. To see those rules, we have to look at what sits inside the machine, not the wires, not the refrigerator, the thing it is protecting. A physical object so alien that the first physicist who truly understood it said the only honest reaction is confusion. His name was Richard Feynman, and he was exactly the kind of person you would expect to crack open the foundations of reality. A Nobel laureate who played bongo drums at strip clubs and picked locks at Los Alamos for fun. In 1981, he stood in front of an audience at MIT and said something that sounded, at the time, like a joke. He said that if you want to simulate nature, if you want to build a computer that can model the way the physical world actually behaves, you cannot do it with a classical machine. Classical machines speak the wrong language. Nature, Feynman said, is not classical. And then he added a word that does not usually appear in physics lectures. He said, "Damn it. Nature is not classical, damn it." He was frustrated. He had spent decades in the quantum world, the layer underneath the one you and I walk around in, and it played by rules no normal computer could capture. A classical computer thinks in bits. A switch, on or off, 1 or 0, and that is it. Every calculation your laptop has ever performed is switches flipping between 1 and 0. Billions of them, very fast, but still just switches. A qubit is not a switch. Both 1 and 0. At the same time, not because we do not know which one it is. Genuinely, physically, measurably in both states, simultaneously. This is not a metaphor for speed. A physical fact confirmed every day in laboratories for over 100 years. The first time you hear it, it should bother you. If it does not bother you, you have not understood it. Feynman said nobody understands quantum mechanics. The best you can do is get comfortable with the confusion. The confusion has a name. It is called superposition, and it changes everything. Superposition was not discovered by theorists sitting in armchairs. It was discovered by two experimentalists who shot silver atoms through a magnet and got a result that made no sense. Otto Stern and Walter Gerlach. Frankfurt, 1922. The experiment was supposed to be simple. You heat silver atoms until they fly off in a beam. You send the beam through a magnetic field that is stronger on one side than the other. Classical physics predicts the atoms should spread out in a smear, like paint sprayed at a wall. Instead, the beam split into two clean dots. Not a smear, but two clean points, as if every atom had made a binary choice, up or down, with nothing in between, and no reason that classical physics could explain. That was strange enough, but the real horror came later, when physicists started asking what the atom was doing before it hit the detector. And the answer, confirmed by a century of experiments since, is that it was not doing either. It was not going up, it was not going down, it was not undecided. It was in both states, simultaneously, as a single physical reality. The act of measurement forced it to pick. Before that, there was nothing to pick between, because both options were equally real. Imagine a coin spinning in the air. While it spins, it is not heads, not tails, something else. A third state containing both. The moment it hits your palm, one answer. But in the air, asking heads or tails is like asking whether blue weighs more than a Tuesday. The question does not apply. A qubit is a coin that never lands until you look. While it spins, it carries two answers. 2 qubits carry 4. 10 carry 1,024. 30 carry a billion. Exponential. But carrying answers is useless if you cannot extract the right one. You need a mechanism that pulls the correct answer from the cloud and discards the rest. That mechanism exists. Older than computers, and it was first demonstrated by a man who was not even a scientist. In 1801, a physician and polymath named Thomas Young set up one of the simplest experiments in the history of science. He cut 2 narrow slits in a barrier and shone a light through them. On the wall behind the barrier, he expected to see 2 bright stripes corresponding to the 2 slits. Instead, he saw a pattern. Bright bands alternating with dark bands, spreading across the wall like the ripples from 2 stones dropped in a pond at the same time. This was interference. The waves of light passing through the 2 slits were overlapping. Where 2 peaks met, they amplified each other. Bright band where 2 peaks met, dark band where a peak met a trough, and the simplicity of it was beautiful. The pure physics of waves made visible. You can see the same thing in a bathtub if you tap the water in 2 places at once. 200 years later, this bathtub effect is the engine that makes quantum computing possible. Here is why. Remember, a qubit in superposition carries multiple answers at once. A system of 300 qubits carries more simultaneous answers than there are atoms in the observable universe. That is not poetry. That is arithmetic. 2 to the power of 300 is a number so large that writing it out would take more paper than exists on Earth. All of those answers exist at the same time inside the machine. But if you just open the box and look, the superposition collapses. You get one random answer out of the pile, useless. So instead of looking, you do something clever. You make the answers interfere with each other. The wrong answers, like the peaks meeting troughs in Young's experiment, cancel themselves out. They destroy each other, while the right answer, like 2 peaks meeting, gets amplified, gets louder, rises above the noise. When you finally measure the system, the right answer is the one left standing. This is not a metaphor. This is the physical mechanism by which a quantum computer solves problems. It sends a computation down every possible path simultaneously, lets the paths interfere, and wave mechanics does the filtering. The machine does not search for the answer. The answer emerges from the collision of all the wrong ones dying. And this is not something only light can do. In 1961, Klaus Jonsson proved that single electrons, fired one at a time through 2 slits, build the same interference pattern. In 1999, Zeilinger in Vienna pushed it further with molecules of 60 carbon atoms, objects you can practically see under a microscope, walking through 2 doors at the same time and interfering with themselves. And this is where the question that unravels everything surfaces. A quantum computer with 300 qubits processes 2 to the power of 300 paths simultaneously. That number dwarfs anything the physical world contains. The paths interfere and produce a verified, correct answer. So where is the computation physically happening? The resources do not exist in this reality. Either the answer is wrong, which it is not, or the resources are coming from somewhere we cannot see. A physicist named David Deutsch stared at this problem for years. Deutsch is unusual even by the standards of theoretical physics. Born in Israel, raised in England, he spent most of his career at Oxford, where he studied under John Archibald Wheeler, the man who coined the term black hole. Deutsch was not interested in building computers. He was interested in what computers reveal about the structure of reality. In 1985, he published the first true quantum algorithm, not Shor's, an earlier, simpler one, designed to prove a theoretical point. And the point was exactly the question we just hit. A quantum computer takes a problem that would require more operations than there are particles in the universe, and it solves it. Correctly. Verifiably. The answer checks out every time. Where did the work happen? Deutsch's answer is the one that nobody wants to hear. The work happened in parallel versions of reality, not parallel in a poetic sense, not parallel as a metaphor for multi-threading. Parallel in the most literal, physical, mathematically rigorous sense available. The computation was distributed across branches of reality that we cannot see, cannot touch, and cannot directly measure, but whose existence is the only explanation for a result that we can see, can touch, and can verify. Think of it like an audit. A company reports 10 billion in profit. You check the books. The company has one factory producing 1 million a year. The numbers do not balance. Either the report is fake, or there are factories you have not found. In quantum computing, the report is real. The single factory is our universe. It does not have the resources. So either the result is wrong and it is not, or there are factories somewhere else. Deutsch called them the multiverse. In 1997, he published The Fabric of Reality. It is the first machine whose operation cannot be explained without parallel realities. The books do not balance any other way. This is where the flaw drops out. You came here because of encryption, and now you are standing in front of a claim that the device threatening your passwords works because reality is not one thing. It is many things, and it reaches into those layers and pulls out answers that a single layer could never produce. If that sounds like science fiction, hold on. What comes next is not a hypothesis. An experiment designed to test whether the universe is what we think it is. The universe failed the test. Deutsch did not invent the multiverse, he inherited it. The idea was born 28 years before the first quantum algorithm, in the most unlikely place possible. A graduate student's dissertation that almost nobody read. His name was Hugh Everett III. Princeton, 1957. 26 years old. His advisor was John Archibald Wheeler, the same Wheeler who later mentored Deutsch, the same Wheeler who named black holes. Everett was trying to solve a problem that had been eating at physicists since the 1920s. The problem was simple to state and impossible to answer. Why does a quantum system behave one way when you are not looking, and a completely different way when you are? The standard answer, the one taught in every physics class at the time, was called the Copenhagen interpretation. Niels Bohr championed it, the most influential physicist alive. Bohr's answer was this: when you measure a quantum system, the superposition collapses. One outcome becomes real, the rest vanish. Do not ask where they go. Do not ask what collapses the wave function. The question is meaningless. Shut up and calculate. Everett looked at this and said no. He said the math does not require a collapse. The equation, Schrödinger's equation, the master equation of quantum mechanics, works perfectly well without it. If you just let the equation run, without adding the collapse by hand, what happens is that every possible outcome occurs. Not one, but all of them. Because the universe does not choose a single outcome, it splits into every possible version, every measurement, every quantum interaction, every moment where a particle could go left or right. The universe branches into versions where it went left and versions where it went right. Both are real, both continue, and neither is more fundamental than the other. Wheeler made Everett cut it in half. Bohr dismissed it personally. The physics community shrugged. Everett left academia, took a job at the Pentagon, never published another physics paper, drank heavily, and died of a heart attack at 51. His instructions were for his ashes to be thrown out with the trash. They were. 40 years later, quantum computing arrived. And the only way to explain what it was doing was the framework of the man whose ashes went out with the garbage. So what does it mean for reality to split? Not poetically. Not as a thought exercise you entertain over a beer and then forget. What does it actually physically, mathematically mean? The answer lives in a mathematical object called Hilbert space. Do not let the names scare you. The idea is simpler than it sounds. Imagine a room. In a normal room, you can describe where you are with 3 numbers. How far left or right? How far forward or back? How far up or down? 3 dimensions. That is the space you live in. Hilbert space is the same idea, but with more dimensions. Many more. For a single qubit, Hilbert space has 2 dimensions. For 2 qubits, 4. For 3, 8. For 300 qubits, 2 to the power of 300 dimensions. A space so vast that no physical analogy can hold it. Here is the key. In Hilbert space, superposition is not magic. It is just a location. A qubit in superposition is a point in a 2-dimensional space, leaning partly toward 0 and partly toward 1. When you measure it, you are not collapsing some mystical wave. You are projecting that point onto one axis or the other. Like shining a flashlight on a ball hanging in midair and looking at its shadow on the floor. The shadow falls left or right. The ball was never on the floor. It was always above it, in a space with more room than the shadow could capture. Now here is what Everett saw. According to Schrödinger's equation, when you measure a qubit, you do not project the ball. You, the observer, the person holding the flashlight, also enter Hilbert space. You become entangled with the qubit. And in the full mathematical description, there are now 2 versions of you. One who saw the shadow fall left, and one who saw it fall right. Both versions are equally real points in Hilbert space. Neither is the original. Neither is the copy. They are branches of the same mathematical object, like a tree that forks. Every quantum interaction is a fork. Every fork is permanent. The branches do not rejoin. They cannot see each other. The version of you that turned this off 3 minutes ago exists in the same Hilbert space as the version still listening. Both are real. Both think they are the only one. The equation makes no distinction. This is not philosophy. This is the math without additions. No collapse, no mystical observer, just the equation running and branching forever. And the machine in the cryogenic chamber, solving problems no single branch has the resources to solve, is the strongest evidence the branches are not a metaphor. But not everyone agrees, and the argument against this picture is not stupid. An old argument, older than Everett, older than quantum computing. It goes back to a hotel in Brussels in 1927, where the greatest physicists alive nearly destroyed their friendships over the question of what reality is. The Solvay Conference, October 1927, brought 29 physicists into a hotel in Brussels, and 17 of them would go on to win Nobel Prizes. Einstein was there, Bohr was there, along with Heisenberg, Schrödinger, Dirac, Born, Planck, Curie, and Lorentz. If you erased that guest list from history, modern physics would not exist. They gathered to discuss the new quantum mechanics, and they could not agree on what it meant. What does a quantum particle do when no one is looking at it? Does it even exist between measurements? Bohr's position was radical in its modesty. The math works, but asking what the electron is doing when you are not looking is not a scientific question. There is nothing there until you look. Stop asking. Calculate. Einstein hated this, not because the math was wrong, because it meant abandoning the idea that the universe exists whether you look at it or not. Does the moon cease to exist when nobody is looking? For an electron, the Copenhagen answer is genuinely, there is nothing there until you look. They fought for 30 years. Einstein designed thought experiments to trap Bohr. Bohr found the escape every time. Einstein could not land the blow. Then, in 1935, he thought he found it. He co-authored a paper with Boris Podolsky and Nathan Rosen that was meant to be the kill shot. The paper described a scenario so strange, so offensive to common sense, that Einstein was certain it would prove quantum mechanics was incomplete. He was certain it would show that there must be hidden variables, deeper rules underneath the quantum randomness, rules that restored a sensible, local, deterministic universe. He called the scenario spooky action at a distance. He meant it as an insult. He had no idea he was describing the actual architecture of reality. Einstein, Podolsky, and Rosen published 4 pages in Physical Review in May 1935, and those 4 pages may be the most consequential in the history of physics. The argument went like this: create 2 particles in a shared quantum state. An entangled pair, then separate them and send one to New York and the other to Tokyo. According to quantum mechanics, neither particle has a definite state until measured. They are both in superposition. But the moment you measure the particle in New York and find it spinning up, you instantly know the particle in Tokyo is spinning down. Instantly, not at the speed of light, not after a delay, but instantly regardless of distance. Einstein said, "Absurd. Information cannot travel faster than light. That is relativity. Either something is traveling faster than light, which is impossible, or the particles had definite states all along, like gloves shipped in separate boxes to different cities. You open one in New York and find a left, so you instantly know Tokyo received the right. No spooky action required, because the gloves were always left and right and we simply did not look." This was the hidden variables argument. Predetermined results, quantum mechanics not wrong but simply incomplete. Einstein was sure of it because the argument was elegant and intuitive, and it was wrong. But proving it wrong took 29 years. Nobody could figure out how to tell the difference. Until a soft-spoken Irishman turned, sat down with a pencil, and found the one thing that would be different. His name was John Stuart Bell. Born in Belfast in 1928, to a working-class family, his father a horse trader. Bell was the first person in his family to stay in school past 14. He studied physics at Queen's University Belfast, then moved to Caen in Geneva, where he spent his days designing particle accelerators and his evenings thinking about the foundations of quantum mechanics. His colleagues considered the evening work a hobby. They were wrong. It was the most important work anyone at Caen would do that decade. Bell was obsessed with EPR, not because he sided with Bohr or Einstein, because everyone was arguing philosophy when they should have been arguing mathematics. Neither side had proposed a way to check. For 29 years. How do you settle an argument about the nature of reality? Not with more philosophy, with a number. Bell broke the loop with a single equation. Published in 1964 in an obscure journal, 6 pages. The idea: if hidden variables exist, there is a mathematical ceiling on how strongly 2 particles can be correlated. Measure one in New York, the other in Tokyo. Repeat thousands of times. The statistics cannot exceed a specific number. Bell derived that number. If quantum mechanics is right, the statistics blow past the ceiling. The math predicts it clearly. For the first time, you had a test. Not philosophy. A number. Below the ceiling, Einstein wins, and you can sleep well. Above the ceiling, the universe is non-local, and the word distance does not mean what you have always assumed it means. Bell published. Then he waited. The experiment was extraordinarily difficult, and it would take 20 years before anyone could do it. The man who did it was a Frenchman named Alain Aspect, working at the University of Paris, and he ran the experiment in 1982. Aspect had been working on the problem since the early 70s. The challenge was not conceptual. Bell had done the hard part. The challenge was engineering. You had to create pairs of entangled photons, send them in opposite directions, measure their polarization at random angles, chosen at the last possible instant so that neither particle could influence the other through any signal traveling at or below the speed of light, and then collect enough data to run the statistics. He did it, and the number was above the ceiling. Not slightly, not ambiguously, but clearly, cleanly, unmistakably above Bell's limit. The correlations between the 2 photons were stronger than any hidden variable theory could allow. Einstein was wrong. The particles were not like gloves. The universe you grew up believing in, the one where things have definite properties whether you look at them or not, failed the test. They did not carry predetermined answers. The correlation was not a product of shared history. It was something else. Something that happened at the moment of measurement. across a distance, with no signal passing between them. But Aspect's experiment had loopholes, tiny gaps a determined skeptic could crawl through. So others followed, John Clauser, Anton Zeilinger, each closing a different loophole, tightening the noose around local realism. In 2015, Zeilinger's group performed the first fully loophole-free Bell test, every escape hatch sealed. The number was above the ceiling, not close. In 2022, the Nobel Prize in Physics went to Clauser, Aspect, and Zeilinger. The universe is non-local, not a debate, not a hypothesis. An experimental result, replicated thousands of times across 4 decades, every loophole closed. 2 particles separated by any distance, connected by something that does not travel between them. The word here and the word there do not mean what they used to mean. Einstein called it spooky. He was right about the spooky part. He was wrong about everything else. So the universe is non-local. 2 particles can be correlated across the width of a galaxy with no signal between them. This is proven. Fine. You could file that under strange facts about physics and move on with your life, except for one thing. The machine we have been talking about since the beginning of this story does not just acknowledge non-locality. It uses it. It runs on it. Entanglement is not a curiosity that quantum computers happen to coexist with. Entanglement is the wiring. In 1993, Charles Bennett at IBM described quantum teleportation, not matter. A quantum state, teleported from one location to another using an entangled pair as a bridge. The measurement destroys the state locally. The information reappears at the destination as if it jumped through a tunnel with no inside. In 2017, a Chinese satellite called MISUS demonstrated this across 1,200 kilometers. Entangled photons from orbit to ground. The particles behaved as one object across empty space. Inside a quantum computer, entanglement does something even more fundamental. Qubits do not work alone. The power of the machine comes from qubits being entangled with each other, so that the state of one is locked to the state of another. When you entangle 30 qubits, you do not have 30 separate coins spinning in the air. You have one object with 2 to the power of 30 faces, all spinning together, all interfering together, all collapsing together when you read the result. Entanglement is what turns a collection of individual qubits into a single quantum system. Without it, you just have a very cold, very expensive box of broken switches. And there is another application that loops back to where we started. Quantum key distribution. A channel that is physically impossible to eavesdrop on. Because intercepting an entangled particle changes its state. The act of listening destroys the message. The same non-locality that breaks the old locks builds new ones that cannot be broken by any machine, now or ever. The thing that kills the old world is the foundation of the new one. But there is a deeper question hiding underneath all of this. By now, the list should unsettle you. Superposition is real, confirmed every day for a century. Interference is real, and it powers the machine that threatens your encryption. Entanglement is real, stamped with a Nobel Prize in 2022. Non-locality is an experimental fact with every loophole closed. The multiverse remains the only accounting that balances the books. Not one of these is a fringe idea. Together, they are the operating manual of reality as we currently understand it. And that manual describes a world nothing like the one you woke up in this morning. So why does the world feel normal? You walk outside. The ground is solid. The sky is one color. Your coffee is either hot or cold, never both. You do not experience superposition. You do not notice entanglement. You have never once looked at a chair and seen it in 2 places at the same time. The quantum world, with all its strangeness, its branching, its non-locality, its refusal to commit to a single answer, seems to be confined to a tiny invisible basement underneath the world you actually live in. Except, it is not confined. It is everywhere. It is the floor and the walls and the ceiling. The reason you do not see it is not that it stops at some boundary. The reason is that something is actively hiding it from you. Something is taking the raw quantum weirdness of reality and smoothing it into the clean, solid, single-answer world your brain expects. And the first clue to how it works comes from the oldest, strangest, most infuriating experiment in all of physics. You already know the experiment, the double slit. We told half the story. The half we left out is what Feynman called the only mystery. Add a detector at one slit, something terrifying happens. The pattern vanishes. Do not watch which slit the particle goes through, you get interference. Both slits? Place a detector, just to know, interference disappears. One slit, one path, as if the universe runs two programs, one for when you're looking and one for when you are not, and looking flips the switch. This has been tested with every quantum object anyone has tried. The result is always the same. Observation changes the outcome. Not observation as in a conscious mind, observation as in information becoming available. The universe behaves differently depending on whether information about the event exists. And that sentence, if you sit with it long enough, will rearrange the way you think about everything. It gets worse. In 1978, John Archibald Wheeler, the same man who mentored Everett and Deutsch, proposed an experiment that should not be possible. He called it the delayed choice experiment. The idea was this: what if you wait until after the particle has already passed through the slits before you decide whether to observe which slit it went through? Think about what that means. The particle has already traveled. It has already passed the barrier. If it went through both slits, it is already interfering with itself. The event is in the past, and Wheeler said it does not matter. You can choose to place the detector after the fact, and the particle will behave as if it knew your decision in advance. If you choose to look, no interference. One slit. If you choose not to look, interference. Both slits. Even though the particle passed through the slits before your decision existed. For 29 years, this was a thought experiment. A provocation. The kind of thing physicists argued about at conferences, and then went home and tried not to think about. Then, in 2007, a team led by Vincent Jacques in France built it. They used single photons and a device that randomly decided, after the photon had already entered the apparatus, whether to measure which path it took. The result confirmed Wheeler's prediction exactly. The photon behaved as if it knew the future. When the detector was switched on after the photon had passed the slits, no interference. When it was switched off, interference. The decision made after the event changed the nature of the event, not retroactively in some hand-wavy philosophical sense. Physically, measurably, repeatedly. The data was clean. You were looking for the catch. There is no catch. The photon does not know the future. What is happening is stranger. The photon does not have a history until the measurement creates one. The past is not fixed. It is contingent on what information becomes available in the present. And the next experiment is worse. It shows that you can erase the information. And when you do, the universe changes its mind. In 1982, two physicists named Marlon Scully and Kai Druhl proposed something that sounds like a magic trick. They called it the quantum eraser. Start with the double slit experiment and place a detector at one slit, so you know which path the particle takes. The interference pattern vanishes. You get classical behavior. The particle picked a slit. One path. No mystery. This is what we just discussed. Now here is the twist. Scully and Druhl asked, what if you erase the information from the detector? Not the particle, not the measurement apparatus, but the information itself. What if you destroy the record of which slit the particle went through, after the particle has already hit the screen? Their prediction was that the interference pattern would come back. In 2000, Kim and colleagues at the University of Maryland built it. Entangled photon pairs. One photon hit the screen. The other was sent through beam splitters that either preserved or erased the witch path information, arriving at its detector after the signal was already recorded. When the information was preserved, no interference appeared in the signal photon, but when the information was erased, interference reappeared. In photons that had already been detected and already recorded. The act of erasing information about the past changed the pattern the past had left behind. Let that settle. This is not delayed choice, where the future decision affects the present event. This is erasure, where destroying information retroactively restores quantum behavior. The universe does not care about observers. It does not care about consciousness. It does not care about detectors or measurement devices or human intentions. It cares about one thing. Does the information exist? If the information exists, classical behavior. If it does not, quantum. And if you create the information and then destroy it, reality switches back, as if the information had never existed at all. This tells us something profound and uncomfortable. The fundamental currency of reality is not matter, and it is not energy either. It is information. The universe is not made of stuff. The universe is made of what is known about stuff. And the rules change depending on whether the knowledge exists. If you are still holding on to the idea that there is one reality out there, solid and objective, and the same for everyone regardless of who is looking, the next experiment takes that away. Eugene Wigner proposed a thought experiment in 1961. Your friend is inside a closed laboratory. She measures a quantum particle in superposition and sees a definite result. Spin up. For her, reality has delivered an answer. But you are outside. You have not opened the door. From your perspective, the entire laboratory is still in superposition. Your friend, the particle, the notebook she wrote the result in, all of it remains in a quantum state. For you, the experiment has no result yet. Who is right? Quantum mechanics says both of you. Not approximately. Both of you are using the correct laws of physics applied to the information available to you. But your facts are mutually exclusive. She says, spin up. You say both are still in play. You cannot both be describing the same objective reality, unless there is no single objective reality to describe. For 58 years, this was a thought experiment, a reason to drink after seminars. Then, in 2019, Massimiliano Proietti and a team at Heriot-Watt University in Edinburgh built it. Entangled photons, multiple observers, a direct test of whether different observers' results can be made consistent within a single objective framework. They could not. The paper was published in Nature. Observer-independent facts may not exist. Not philosophically, experimentally, measured, published, and replicated. The universe may not have a view from nowhere, only views from somewhere, and those views do not have to agree. This is the deepest point of the spiral. We came here following a machine that cracks encryption, and we have arrived at a place where the word real does not mean what it used to mean. But chairs still hold you up. The world still feels solid. If all of this is true, something must be packaging the quantum chaos into the stable, normal-looking world you experience every second. Something is, and it has a name: decoherence. The word sounds technical. The idea is not. It is one of the simplest and most unsettling explanations in all of physics, and it answers the question you have been carrying since we entered the quantum world. Why do I not see any of this? A German physicist named Heinz Dieter Zeh first glimpsed the answer in 1970. Zeh was an outsider. His ideas were ignored for over a decade. The physics community was so committed to the Copenhagen interpretation, to the idea that you should not ask what happens between measurements, that anyone who tried to answer the question was treated as a crank. Zeh answered it anyway. He showed that a quantum system does not exist in isolation. It interacts with its environment, and the interaction starts small. A photon bounces off the system and carries away a trace of its quantum state. Then an air molecule collides with it and takes another trace. Then thermal vibrations pass through the surrounding material and spread the traces further. Each interaction is tiny, insignificant on its own, but each one leaks a sliver of information about the superposition into the surrounding world. And once the information leaks, the superposition does not collapse. It drowns. Think about it this way. You are standing in an empty cathedral. You whisper a word. Clear. Every consonant. Now imagine the same whisper in a crowd of 8 billion people, all talking at full volume. Your vocal cords vibrate the same way, but no one hears you. Not because you stopped, because your signal dissolved into the noise. It is not gone. It is lost. That is decoherence. A qubit in superposition is the whisper. The environment is the crowd. The moment the qubit interacts with anything, the superposition leaks into the surroundings and becomes undetectable. Not destroyed, but diluted past the point of recovery. From our perspective, it looks like the qubit chose one state. It looks classical. This is why chairs are solid. Not because quantum mechanics stops at the scale of a chair. It never stops. But a chair is trillions of atoms, constantly bombarded by photons and noise, and the decoherence time is so short, it might as well be zero. The superposition drowns before you can blink. And this is what a quantum computer is fighting against. The cryogenic chamber, the vacuum, the shielding. All of it exists for one reason: to keep the crowd silent long enough for the whisper to finish its sentence. How long does the whisper last? For a chair, a table, a human body? The answer is almost no time at all. Femtoseconds. A femtosecond is to a second what a second is to 32 million years. At the scale of everyday objects, decoherence is so fast it might as well be instantaneous. The quantum state exists and then it is gone, swallowed by the noise of the environment before anything interesting can happen. This is why you have never seen a chair in two places at once. Not because the physics forbids it, because the physics allows it for a window of time so absurdly short that the universe itself barely notices. But for a qubit, the window is longer, not much longer. Microseconds. Sometimes, in the best laboratories on Earth, milliseconds. A millisecond is not a long time. You cannot snap your fingers in a millisecond. But it is long enough. Long enough for a quantum computation to run, for interference to do its work, for the paths to collide and the right answer to emerge. The entire art of quantum computing is the art of keeping that window open. Every fraction of a microsecond you gain is a fraction more of reality you can use before the crowd drowns out the signal. This is what the cryogenic chamber is for. The machine operates at 15 millikelvin. That is 15 thousandths of a degree above absolute zero. Colder than the vacuum of deep space. Colder than anything in the natural universe. At that temperature, thermal vibrations nearly vanish. The air molecules are gone because there is no air, just vacuum. The electromagnetic noise is suppressed by layers of shielding that would make a bomb shelter jealous. The qubit sits inside this fortress of silence, isolated from the rest of the universe as completely as human engineering can manage, and even then it only stays coherent for a fraction of a second. A quantum computer builds a tiny pocket where superposition survives long enough to finish the calculation. The engineers are not building a faster calculator. They are building a room where the mask comes off for a few microseconds before decoherence slams the door shut. Every advance is a battle to keep that door open longer. Willow did not just reduce errors, it extended the time it can think before the universe interrupts. But Wojciech Zurek, the physicist who formalized decoherence in 1981, was not satisfied with the simple version of the story. The simple version says, the environment destroys superposition. Noise kills the signal. End of explanation. Zurek looked at this and saw something deeper. He asked a question nobody else was asking. If the environment kills superposition, why does it always leave the same survivors behind? Why do chairs come out solid every single time instead of dissolving into some other configuration? The answer he arrived at, published in 2009, he called quantum Darwinism. The name is not a metaphor, a direct analogy to biological evolution, and a precise one. Zurek showed that when a quantum system interacts with its environment, the environment does not erase the superposition blindly. It selects certain states, The ones robust against photon bombardment and thermal noise survive. Everything else dissolves, and what remains, what he called pointer states, is the only version of quantum reality that the classical world ever gets to see. Your chair is solid, not because solidity is a fundamental property of the universe. Your chair is solid because the quantum state corresponding to solidity is the one that survives decoherence. Among the trillions of possible quantum states the atoms in your chair could occupy, the overwhelming majority dissolve on contact with the environment. The one that persists, the one that gets copied and amplified and spread across every photon bouncing off the chair, is the state you call solid, brown, wooden here. It won. Not because reality chose it, because everything else lost. This changes what the classical world is. It is not the ground floor. It is not the foundation, the top layer, the residue, the survivors of a selection process that happens at every scale, at every moment, in every atom, trillions of times per second. Underneath it, the full quantum reality is still churning, branching, interfering, being weird. You just cannot see it because the environment has already picked the winners by the time the information reaches your eyes. So where is the border? If decoherence is a matter of scale and speed, not a fundamental law, then there must be a line somewhere, a size at which quantum stops and classical begins. Physicists looked for that line. They did not find it. In 1999, Anton Zeilinger's group in Vienna sent molecules of carbon-60 through a double-slit experiment. Carbon-60, Buckminster fullerene, 60 atoms arranged in a sphere the shape of a soccer ball, a molecule large enough to see under an electron microscope. They fired these molecules one at a time through the slits. The interference pattern was clean, unmistakable. A molecule made of 60 atoms walked through two doors at the same time and interfered with itself, just like a photon, just like an electron, just like Young's light in 1801, but not a point particle, not an abstract wave, a physical object with a shape and a mass and a chemical formula that you could write on a napkin. In 2011, Markus Arndt, also in Vienna, pushed it further. His team demonstrated interference with molecules containing over 430 atoms. Complex organic molecules, objects that by any everyday standard are stuff. Tangible, real, and they were in superposition. Both paths at once, interfering with themselves, behaving as if the word here did not apply to them. The record keeps climbing. Every few years, a bigger molecule. Each time, the same result. Interference, as if size made no difference, as if the quantum world did not know it was supposed to stop at some boundary. The line between quantum and classical does not appear. It does not exist. There is no wall. There is only decoherence getting faster as objects get larger, drowning the signal before anyone can detect it. But the signal is there. There is no size limit on superposition. The equations do not discriminate. The only thing preventing you from seeing a planet in two places at once is that the decoherence time is so short, the superposition dissolves before a single photon can carry the information to your eye. The world is not classical. The world is quantum, moving too fast for you to catch. The machine in the cryogenic chamber slows it down long enough to see what it actually looks like underneath. A surface that is not a floor. It is a mask. And the machine that lifts the mask can do something else with the view. Remember Feynman. In 1981, when he stood up and said, "Nature is not classical," he was not just complaining. He was pointing at a specific problem that classical computers could not solve. The problem was simulation. Not simulation in the movie sense. Simulation in the physics sense. Predicting how a quantum system will behave by modeling every interaction between every particle. Why does this matter? Why should you care about simulating molecules? A molecule is a quantum system. The atoms in a molecule are held together by electron bonds, and those electrons obey quantum mechanics. If you want to predict the behavior of a new molecule, a drug candidate, a catalyst, a superconductor, you need to model those bonds. A classical computer can handle small molecules, hydrogen, helium, a few atoms, but the number of quantum states grows exponentially with every atom you add. By the time you reach about 50 atoms, the number of states exceeds what any classical computer can store, let alone calculate. 50 atoms. A molecule smaller than a grain of sand. This is not a limitation of our computers. It is a limitation of classical computation itself. You cannot simulate a quantum system with a classical machine because the classical machine does not have access to the same physics. It is like trying to predict how water flows by pushing coins around on a table. The coins do not flow. They are the wrong kind of object. A quantum computer uses the right kind of object. Its qubits obey the same laws as the electrons in the molecule. Superposition, entanglement, interference. The machine does not calculate the behavior of the molecule, it mirrors it. It becomes a small version of the same physics, and the answer emerges from the machine the same way it emerges from nature, by letting the quantum states evolve and interfere. In 2020, Google simulated the electronic structure of a chain of 12 hydrogen atoms, a simple system that pushes classical methods to their limits. Alan Aspuruguzik, a chemist who has spent his career at the intersection of quantum computing and chemistry, calls this the real revolution. Not cracking codes, modeling molecules, new drugs designed by machines that think in the same language as the molecules, new materials with properties no classical method could predict, new catalysts for reactions we could never model. The entire field of chemistry, stuck using approximations since its birth, is about to get a machine that does not approximate. It solves. The same machine that threatens every lock on Earth could redesign the molecules in the medicine you take. The thing that splits the old world open is the same thing that assembles the new one, because it speaks the language that the universe is actually written in. But speaking a language is not the same as only speaking it. If the machine can talk to molecules, it can also listen. The same superposition that powers computation powers measurement. A qubit is the most sensitive object humans have ever built precisely because it is the most fragile. Every stray photon, every thermal whisper, every gravitational ripple nudges it. That fragility is the enemy inside a quantum computer. But fragility is not a flaw. It is a feature with two faces. Put that same sensitivity to work as a sensor, and it becomes something else entirely. It becomes an ear pressed against the wall of reality, hearing things no classical instrument can detect. An atomic clock at NIST uses superposition to measure time with a precision that would not drift by a single second in 15 billion years, longer than the universe has existed. A quantum gravimeter can feel the pull of a buried tunnel from the surface of the road above it. Not by digging, but by listening to the shape of the gravitational field with an entangled atom that notices what a classical sensor would miss. A quantum magnetometer can detect the firing of a single neuron inside a living brain. Not through surgery, but through silence, and a qubit tuned so finely to the magnetic field that the tiny electrical pop of one nerve cell is enough to move the needle. This is the same physics, the same superposition, the same entanglement. The thing that breaks your encryption also measures time more precisely than anything in the observable universe. The thing that cracks the bridge also maps the inside of your brain without touching your skull. And here is the part that should twist your expectations into a knot. That fragility, the very thing that makes a qubit so hard to keep alive inside a computer, is also the thing that makes it impossible to steal. Because you cannot touch a qubit without changing it, and you cannot copy it at all. This is not a design choice. It is not a feature that some clever engineer added. It is a law. In 1982, 3 physicists working independently, Wouters, Zurek, and Dijks, proved what is called the no-cloning theorem. You cannot duplicate an arbitrary quantum state. Not with a better machine, not with more energy, not with technology 1,000 years more advanced than ours. The universe will not let you. baked into the mathematics the way the speed of light is baked into relativity. Not a wall you can climb with a taller ladder. The absence of a direction called up. What does this mean for the story we have been telling? What happens to Harvest Now? Decrypt Later when copying becomes impossible? RSA, the bridge, the lock, the whole system that is cracking under the weight of Shor's algorithm was built on a mathematical assumption. Factoring is hard. That assumption held for 50 years. It is about to fall. But the no-cloning theorem is not an assumption. It is a physical law. And physical laws do not fall. They do not get revised by a smarter algorithm or broken by a faster machine. They are the rules. Not our rules. The rules. Remember the harvest? The whole nightmare exists because copying classical information is free and invisible. You tap the wire. Nobody notices. Copying quantum information is impossible. Intercept an entangled photon and it changes state. The entanglement breaks. The receiver sees it immediately. Like trying to photocopy a soap bubble, the bubble pops. Wigner, one of Feynman's students, saw this in 1970. He proposed quantum money, currency that physically cannot be counterfeited, because counterfeiting is copying and copying is what the universe forbids. The idea sat in a drawer for decades. Now the technology exists. The lock that is breaking was built on math. The lock that replaces it is built on physics. And that difference is the difference between a wall that might crumble and a wall that cannot exist in a broken state. But here is the thing about walls. Even the ones that cannot crack have a height. And the universe has been very specific about where the ceiling sits, because there is a cost to thinking. Not a metaphorical cost, not the cost of coffee and electricity and graduate students, but a genuine physical cost. A tax levied by the universe on every computation ever performed or ever to be performed. How much does it cost to think? Is there a price tag on forgetting? In 1961, Rolf Landauer at IBM proved that erasing one bit produces a minimum amount of heat. Not inefficiency. Physics. Information is physical. The formula fits on a coin. K times T times ln2. What it tells you is simple. The hotter your environment, the more it costs to forget. Bennett showed in 1973 you can dodge the tax by never erasing. But deferral is not escape. Debt in a different currency, because reversible computation demands infinite memory, and memory is matter, and matter costs energy. Which brings us to the deeper limit. Even before Landauer, Bremerman had shown in 1962 that there is a maximum speed at which any physical system can process information, set by the energy it contains. Lloyd at MIT calculated the ultimate laptop, 10 to the power of 50 operations per second. Incomprehensible, and still finite, still inside a cage. A quantum computer harnesses interference, entanglement, and superposition, and that combination makes it exponentially more powerful than any classical machine. But exponential power is still power inside a cage. The multiverse might be the engine. Entropy is the brake. The universe gave us superposition with one hand and wrote the invoice with the other. And the price brings us back to the bridge. Because inside these limits, the quantum computer will eventually break RSA. That is not a question. It is arithmetic. The machine is scaling. The algorithm is waiting. The old lock will fall. The only question is whether the new lock will be in place before it does. Someone built a new lock. It is not theoretical. It has a name, a standard, and a deadline. In 2016, NIST launched a competition, an open call to mathematicians and cryptographers from every country. Build us an algorithm that a quantum computer cannot break. Can you build a lock that resists quantum acid? The competition ran for 8 years. Dozens of candidates entered, and teams from universities, corporations, and intelligence agencies spent years trying to crack each other's submissions until most broke and a few survived. The survivors are built on lattice problems. Imagine you are standing in a grid of points in 3-dimensional space. Finding the shortest path is easy. Now imagine the same grid stretching into 500 dimensions around you. The shortest path is still there. The math guarantees it exists. But finding it, actually calculating which route is shortest through a forest of 500 dimensional intersections, is a problem that neither classical nor quantum computers can solve efficiently. Shor's algorithm, the acid that dissolves RSA, does not work here. Different mathematical structure, different terrain entirely. The acid hits the lattice and nothing happens. In 2024, NIST announced the winners. Crystals Kyber for key exchange. Crystals dilithium for digital signatures. The names sound like science fiction, but the math underneath them has been tested, attacked, and stress-tested for nearly a decade by the best cryptanalysts alive. The new standard is published, the new lock is cut, and the migration has begun. But migration is not a switch you flip. At every server on Earth, every satellite in orbit, every embedded chip in every medical device and weapon system, all of it runs on RSA or ECC. Some cannot be updated. The hardware predates the threat, and those systems have to be physically ripped out and rebuilt from scratch. This takes decades, and while the decades pass, the harvest continues, the margin shrinking every day, new secrets flowing through old pipes. The race is a slow, grinding, narrowing corridor against a clock that does not care about budgets or the fact that the person who designed your building's security retired 15 years ago and nobody has the password. The question is whether the new lock gets installed before the old one breaks. Right now, nobody knows. The arithmetic is uncomfortably close. Stand back for a moment. Not from the math, from the timeline. In 1900, Planck introduces the quantum as a desperate trick, and by 1922, Stern and Gerlach discover it is real, and in 1935, Einstein tries to kill it with EPR, and accidentally describes the architecture he was trying to disprove. In 1957, Everett proposes the multiverse and is laughed out of physics. In 1964, Bell finds the test. In 1982, aspect proves reality is non-local. In 1994, Shor writes the algorithm and then the acceleration. 2019, Sycamore. 2022, the Nobel Prize. 2024, Willow. 125 years. What species does this in 125 years? What species goes from a desperate trick to a machine that reaches into the basement of reality in the time it takes a redwood to grow? We are not the smartest species to have lived on this planet. We are the first to reach into the basement. Not the first on Earth. The first anywhere we have ever looked. We have found no signal from the sky, no artifact on Mars, no footprint on any moon of any planet around any star we have ever observed. As far as we can tell, we are the first piece of matter in the observable universe that looked at the rules governing its own existence and built a tool that exploits them. We did not just discover that reality has a basement. We built a machine that works down there. And what we found in the basement is not what we expected. We expected a faster computer. We found a universe that is non-local, possibly branching, governed by information rather than matter, and quite possibly lacking a single objective reality that all observers share. We found that the classical world, the solid, sensible, single-answer world you wake up in every morning, is not the foundation, the top layer, the residue, the mask. The machine that threatens your bank account is the same machine that revealed the mask. And now there is one last question the machine might eventually answer. The strangest one. The one about us. The question is simple, and it might be unanswerable, but the machine we have been building might be the first tool that can take a serious run at it. Here it is. If observation changes reality, and we are the observers, what are we? Think back. What has been standing at the center of every experiment we walk through? In the double-slit experiment, observation collapses the interference pattern. In the delayed choice experiment, a future observation rewrites the past. In the quantum eraser, destroying information restores quantum behavior. In Wigner's friend, two observers see mutually exclusive realities, and both are right. Every time we peeled back a layer, the observer was standing there, at the center of the machinery, not as a passive witness, but as an active ingredient. The universe does not seem to run the same program when no one is watching. The question is whether that means anything about the watcher. Roger Penrose thinks it does. Penrose, the Oxford mathematician who shared the 2020 Nobel Prize in Physics for his work on black holes, has spent decades arguing that consciousness is not a classical process. In 1989, he published The Emperor's New Mind, where he proposed that human awareness arises from quantum effects in the brain, not from neurons firing like transistors, from something deeper, something that operates at the boundary between quantum and classical, in the same territory where decoherence turns superposition into the solid world you see. Stuart Hameroff, an anesthesiologist at the University of Arizona, gave Penrose's intuition a physical address: microtubules inside neurons, tiny protein tubes that form the scaffolding of every cell. Hameroff and Penrose proposed that superposition occurs inside them, and conscious experience corresponds to the moment of decoherence. The theory is called OR, 30 years of criticism and refinement, not proven, not disproven. In 2015, Matthew Fisher proposed a different mechanism: nuclear spins of phosphorus atoms in Posner clusters, with coherence times long enough for quantum processes to influence neural activity. Younger, more speculative, but specific enough to be wrong, which in science is the highest compliment. None of this is settled. We do not know whether consciousness is quantum, but the question is no longer philosophical, it is experimental. It has predictions that can be tested. And the machine that might test them is the same machine that started this story by threatening to break every lock on Earth. Remember what the machine does. It simulates quantum systems. Molecules, materials, chemistry that classical machines cannot touch. But a microtubule is a quantum system, the same kind of system you carry in every cell of your body. A Posner cluster is a quantum system. A neural network operating at the boundary of decoherence is a quantum system. If Penrose is right, or if Fisher is right, or if someone we have not met yet proposes a third mechanism that turns out to be closer to the truth, then this machine is the first instrument that could simulate consciousness at the level where consciousness might actually operate. Not model it, not approximate it with statistics the way a classical neural network does. Simulate it. Run the same physics. Let the qubits do what the microtubules do, or what the phosphorus spins do, and see what happens. See if awareness emerges from the math the same way interference emerges from the double slit. Not because you programmed it to, because the physics produces it. We built this machine to break a lock that had held for 50 years. That was the purpose. That was the funding. That was the reason your tax dollars flowed into cryogenic chambers and your government poured billions into error correction and lattice cryptography and the long grinding race between the old lock and the new one. And the machine might turn around and answer a question that has haunted every conscious being since the first one opened its eyes. What am I? Why am I aware? Is awareness a product of computation, or is it something that the universe does at a deeper level than computation can reach? The gun that was built to break the bridge might turn out to be a mirror, and the face looking back might be the first clear image we have ever had of ourselves. Let us go back to the bridge, not the metaphor, the real thing, the mathematical structure that holds the digital world together. RSA ECC, the single point of failure system that protects every secret your civilization has generated since the invention of the internet. The crack is real, the machine is scaling, the harvest is ongoing, and the new lock exists, but the migration is painfully slow. These are facts rather than speculation, unfolding right now in laboratories and server rooms, and intelligence agencies while you are listening to this. The same world where your coffee is getting cold and your phone is buzzing with a notification you should probably check. But here is what changed. When we started this story, the crack in the wall was the point. The danger was the point. The machine was a threat, a weapon aimed at the foundation, and that has not changed. The harvest is real and the vulnerability is real. The arithmetic of migration versus maturation is real and it is tight. But you followed the crack down. Through the wall, through the mathematics, through the machine, into the qubit, into superposition and interference and entanglement, into the multiverse, into delayed choice and the quantum eraser and the death of objective reality, into decoherence and quantum Darwinism and the disappearance of the border between quantum and classical, into the limits of computation itself, into the question of what consciousness is and whether the machine that breaks your password might also explain your mind. The crack in the wall was not a failure. It was a door. Not a door we designed. Not a door we expected. A door that opened because we built a machine to break a lock and discovered that the lock was attached to something much larger than a door. It was attached to the architecture of reality. And when the machine forced the lock, it did not just open the vault, it opened a view. Here is what you see through the door. The universe is not what it looks like. The solid, singular, common-sense world that your senses deliver to you every morning is a surface. Underneath it, reality is non-local. Two particles separated by a galaxy are connected by something that does not travel between them, and the word distance does not apply. And if distance is an illusion, then the universe is far more connected than it looks, which means it can branch. Every quantum event a fork, every fork permanent. The version of you that turned this off 20 minutes ago mathematically as real as the one still listening. And if it branches, what determines which branch you see? Not matter. Information. The past is contingent on what information exists in the present. And if information governs reality, then objective reality, the kind that is the same for everyone, may not exist at all. Because two observers with different information can hold mutually exclusive facts and both be correct. And if objectivity falls, what is left? A residue. What you see is what survived. Solidity is not a fact. A survivor. And the device that showed us all of this is the same one about to break the lock on every digital secret you own. The telescope and the weapon are the same object. What reveals the basement is what breaks the floor. Was any of this supposed to happen? The engineers wanted a faster computer. The cryptographers wanted a better lock. The physicists wanted to simulate molecules. Nobody set out to discover that reality has a mask. But it does not care what you set out to discover. It operates on the actual rules. And the actual rules turned out to be stranger than anyone involved was prepared for. So, what do you do with this? You woke up this morning in a world that felt solid. You drank something. You checked your phone. The screen was bright and the floor was under your feet, and the walls of your room were exactly where you left them. Nothing about your Tuesday suggested that the universe is non-local, that reality might branch every time a particle makes a choice, that the past can be rewritten by erasing information in the present, or that the chair you are sitting in is not truly solid, but is instead the quantum state that happened to survive a selection process running trillions of times per second in every atom underneath you. Nothing about your Tuesday suggested any of that, and nothing about your Wednesday will either. That is not because the science is wrong. Everything we walk through is real, confirmed, replicated, Nobel Prizes awarded. The universe really is that strange. But strangeness does not reach up. Decoherence makes sure of that. The noise of 10 to the power of 23 particles drowns every quantum whisper before it reaches the scale where your eyes and your coffee operate. You will never see your chair in two places. The basement is sealed, not by a lock, but by the sheer volume of the crowd. Your life does not change because of what you learn today. Knowledge is not danger. It is weight. Your bank account is still there. Your locks still hold. The harvest is real, but it is a problem for cryptographers and governments and systems engineers, not for you brushing your teeth. The migration to post-quantum encryption will happen. It will be slow. It will be messy. Some things will break. Most will not. The new lock is built on physics, not on math, and physics does not bend. But something did change. Not in the world. In you. You know now. You know that the machine your government is racing to build and racing to defend against is not a faster computer. It is a device that operates in the basement of reality, using rules that the world you see does not appear to follow, pulling answers from a space that might contain more versions of the universe than there are atoms in any single one of them. You know that the floor you're standing on is not the bottom. There is a layer underneath, and underneath that, another. And the further down you go, the less the world looks like the world. Because things become less solid, then less singular, then less local, and finally less objective, until what you're looking at does not resemble the surface at all. The deeper you dig, the more the universe looks like something made of information rather than stuff. Something that behaves differently depending on whether anyone is keeping records. Something that might not have a single story at all, only billions of stories. Branching, interfering, selecting, and producing the thin, stable, classical surface that your senses are evolved to navigate. You did not need to know this. You could have gone your entire life without learning that a silver atom passes through a magnetic field in 2 directions at once, or that a photon's path changes based on a choice made after it has already arrived, or that 2 observers can disagree about a fact and both be right. You would have been fine. The sun would rise on schedule. The people you love would still be there when you got home. But you know now. And there is something in that knowledge that is not frightening. Not anymore. You passed through the fear somewhere around the time the locks started breaking, and the multiverse opened up, and the border between quantum and classical disappeared. The fear was real while it lasted. But on the other side of it, there is something else. Wonder. That is the word. Not terror, not nihilism. Not the grim resignation of a species that discovered it is standing on a trapdoor. Wonder. The kind that comes from realizing the thing you live inside is incomprehensibly more complex, more layered, more deeply structured than anything you were equipped to imagine. The kind that does not shrink you, not smallness, location. You are here. A biological organism. Carbon and water. A product of quantum chemistry so complex that no classical computer will ever simulate the molecule that carries your genetic code. Standing on a planet that condensed out of a dust cloud governed by the same quantum mechanics that powers the machine in the cryogenic chamber. Looking up at a sky full of stars whose light traveled as both a wave and a particle to reach your retina. You are not separate from this. You are this. You are quantum mechanics, walking around, asking questions about itself. And you built a machine that can look at itself. That is not a small thing. In the entire history of matter in the observable universe, stretching back 13.8 billion years, no piece of that matter has ever, as far as we can tell, constructed a device that deliberately exploits the quantum foundations of reality to perform computation. Rocks did not do it, stars did not do it, galaxies did not do it, but you did. It breaks locks. It reads the basement. It might one day simulate the process that produces the experience of being you. It is dangerous and extraordinary, and the fact that it exists at all is, if you let yourself sit with it for a moment, the most improbable thing in the visible universe. The wall has a crack. That is where we started. The crack is real, the machine is real, and the harvest is real. The race between the old lock and the new one is real, and it is close. These things matter. They will shape the next 20 years of security, diplomacy, intelligence, and trust. People in rooms you will never enter are working on it right now. They will keep working on it tomorrow. But the crack goes deeper than anyone planned. It goes through the mathematics, through the physics, through the architecture of reality, all the way down to a basement where the rules are not what we thought they were. And the device that opened the crack did not just reveal a threat, it revealed a world. You are still here. The floor is still solid. The coffee is cold by now, but the mug is still in your hand, and the morning is still doing what mornings do. Nothing about your life needs to change because of what you heard. But the next time you set down a cup on a table and hear the small, solid, reassuring sound of ceramic meeting wood, know that underneath that sound, underneath the atoms in the ceramic, and the atoms in the wood and the atoms in the air that carried the sound to your ear, there is something else. Something non-local. Something branching. Something that behaves differently when information about it exists. Something that might not have a single story. Something that a machine in a cryogenic chamber, colder than the space between the stars, is only just beginning to read. You are fine. You are here. The world is holding. And underneath it, the universe is doing something extraordinary,